Okay, so we started talking about the implementation of the directories. Directory is a special file in it. There is a special block, and in that block you have the information about the directory entries. And one of the things to make a decision on is to decide whether we should support variable length file names. I mean, for some file systems, for example, the early MS-DOS file systems, the file names are the length of the file names are fixed, 8 characters, nothing more, nothing less, and three letters of extension, and that was it. Later they decided that this is not enough. Maybe we should have variable length file names, and we discussed this last week's lecture in implementing the directories. Okay, so when we okay, so then we started talking about different aspects of implementation of these directories and the implementation details. Okay, one of the details of implementing directories is if you have thousands of files in a single directory. Okay, if you have thousands of files in a single directory, then when you make a search, it's going to take lots of time. Okay, so linear searching can be slow. So what are we gonna do? I mean, if you have more than 1,000 files in a directory, okay, some people have suggested that let's use hashing. Okay, so how does the hashing work? You take the file name and you hash it using a simple hashing function, and you look up the hash index in the hash table. Okay, and you keep a hash table in your directory. As you know, adding elements to hash tables or removing them or making a search, they are all O1 operations. Uh, that's very efficient. And if you like to do listing all the files, then that's possible too. And if you like to keep them in some sorted order, that's possible too. Okay. So that's the idea of using the hashing for making the searching faster in directory implementations. And the other idea is, since directories are files, you open them, right? When you open them, you keep all the file information in your memory in a cache. So if you keep them in a cache, if you keep them in a cache in memory, then all the searching, all the directory processing will be very efficient, because you don't have to go to the desk all the time whenever there is a need for making a search. For example, when I when I open my shell, okay, I know that this directory is open. This is because this is my current directory, and when I switch to other directory like that one, this is open too. So it would be logical to have these two directories, this directory and my parent directory, keep it open. They have to be opened, and keep their contents in my memory. So that would be very fast when I try to load some file or get some information about the file. Okay, so these are some optimization techniques for the directories, and depending on your file system, some of them are already implemented. Okay, good. Another topic is shared files. Okay, remember sharing files between two users, between two directories. For example, I have three users: user A, user B, and user C. Okay, and they have their own files, they have their own directories. And if these two users, B and C, like to share this file, using using hard linking hard linking or soft linking, doesn't matter. They like to share a file like this one. Okay, how would I implement this? I cannot list this file as the block addresses under these two the directories. That would make it a little bit difficult to append more information to that file. So we need to be careful here. The other problem is who is going to be the owner of this file. Okay. With the inode solution, you don't have that block problem because all you need to do is you just keep the inode of this file inside the directory of this C and inside the directory of this B. That's it. So inode solve this problem because each file has a main inode, and that inode keeps all the file attributes and the block addresses and etc. So inode solution solve this problem of repeating the same blocks in these two different directories. But the problem of ownership, we have to be careful. Okay, we have to be careful. What do I mean by problem of ownership? This is C's directory. Okay, C says that I am the owner of this file. Okay, in the I know this says that. So later I share this file with other user B. Now inside my inode, I need to keep this information. Two different positions I am keeping a pointer to this file. Later, if I delete this file from C's directory, the original owner, I get this picture. I have a file under B's directory whose owner is C, and there is no other there is no other pointer to that file. Okay, so this is simply possible, but you should have a specialized inode structure to keep this picture valid all the time. So inode idea is really nice. You don't keep much information in the directory entries. For example, remember this one in the way we keep directories as files. So you have a pointer to file name and you have the file one attributes and etc. With the inode implementation, you don't need any of these. So all you have is the inode numbers of all the files in that directory, and all the attributes and everything is kept inside the inode itself. So sharing is very easy. And making this kind of file sharing scenarios possible. Okay, so
Question: why is having a file owned by C in B's directory a problem?
I didn't say it's a problem. I said that we should let it happen. I mean, this should be possible.
Okay.
So you cannot assume that since these files are under C's directory, you cannot assume that these files all belong to the same user C. There should be ways of having different owners under different directories. Even the owner doesn't know that it owns the file. Okay, that's what I'm saying. So this kind of sharing wouldn't be that easy if I keep all the file related information in the in the directory itself. So keeping these kind of attributes in the inode solve this problem. That's what I'm saying. Okay, there are many different issues with the implementation of the file systems, and we touched up only a few of them, and I'm not going to go into details of it. There are specifications of different file systems, for example, FAT32, FAT16, different FAT systems, and the specifications say that this has to be like this way and you implement it that way. So the specification of the FAT systems are available and you are allowed to implement them. You are allowed to implement them. You are allowed to use them in your you are allowed to use them in your own system without any copy protection or without any patenting issues. Okay, there is an idea. The idea is this. We are going to discuss this under this log file systems. Um, Reading is becoming more and more efficient from the mechanical hard drives. Why? Because on a mechanical hard drive, they have very large buffers. Okay, they have very large buffers. What do you mean by buffers? They read the data from the disk to the hard disk buffer. Let's say my hard disk has 1 GB of data buffer. So because of the locality principle, okay, when you make a disk read, usually you read related data, and if you keep the related data in your cache, then reading becomes so efficient. Reading is so efficient. So most of the time when you do reading, you read from the cache of the buffer of the hard disk. You don't need any mechanical movements of the hard disk. That's it. That's good. But when it comes to writing to disk, things are different because you cannot keep your data on the cache. You have to write it. You have to write it back because that information is very important. If there is a crash, there is a risk of losing all the data. You cannot keep the modified data in your cache for a very long time. From time to time, you need to write it. Okay, so that's what we are saying. Okay, CPUs get faster, RAM memories get larger. Okay, disk caches are also increasing rapidly. So we say that most of our reads are coming from the system cache, but for the writes, okay, we need to write it back. So this is what they say. We do the writes, okay, in the buffered memory, and periodically all the buffered writes are written to the disk as a single segment. You don't put them, okay, you don't put them, you don't put the data back to the original places, but you put on different places on the hard disk. You will say that for the last 5 seconds, the data that is modified data is this, and I'm writing this to this track. And writing would be very efficient because you are writing them to the same place. Reading this time is going to be difficult. Why? Because you need to look for the modifications for your file. Okay, but as we said before, reading is so efficient because most of the time reading is going to happen from the cache. So that's the solution that they found. Okay, let's take the advantage of the cache. Okay, when we try to write something to the disk, keep it in the memory for a while and write it back to the disk as a single segment. So repeat, you are not writing the data, your file, back to the original place, but you are writing it to some other place, the modification with the modifications. And keeping track of this information may not be easy, but overall this is more efficient given the cache amount, given the speeds of the CPU and etc. So these are called log file systems. Of course, these are specially developed for the mechanical disks, okay, mechanical hard drives. And since nowadays we are using the solid state drives more and more frequently, this log file system doesn't make much sense for the SSD storage units. Okay, of course, that doesn't mean that it's not useful because all the servers, this servers, CPU servers, they still use mechanical hard drives because their price per gigabyte value is better than the SSDs, and they have some other advantages too. Okay, so this is the log file systems. This is just the concept of file system implementation. Another file system implementation idea is the journaling file systems. Journaling file system is doing this. Okay, we weren't that careful about what happens to our data if the system crashes when it comes to memory, right? Okay, when we are writing to the memory or when we are reading from the memory, we don't think much about what happens if the system crashes while I am doing this. Because if the system crashes, all the data is discarded anyway. So what are we going to do? We can't do much. But with the files, with the file systems, it is important. For example, let's look at this one. This is how you remove a file in Unix. Okay. When I say remove this file from this directory, I take I take the inode number of that file from my directory. So I erase it. And then I release the inode to the pool of free inodes. So I say that I don't need this inode anymore. So I am returning it. And after that, all the blocks that belong to that file has to be returned. It has to be marked one by one. So this thing is just maybe a simple operation. Maybe this thing is a simple operation. And this will require me mark many blocks as free. Okay, so what happens if my system crashes while I am in between these two steps, or while I am in between these two steps, or see, this is a very large loop. Okay, I keep returning all those blocks one by one. So if my system crashes while I am doing any of these, then I would leave my file system in an inconsistent state. That's not a good thing, because maybe I removed the inode, okay, I removed the file from my directory, but inode is still there. So even though I don't have that file in my directory, the file stays in the disk, okay? It occupies place, and the bad thing is that nobody has any information about it. And I release the inode, but now the blocks are there. So these are all bad stuff. They create lots of inconsistency and inefficiencies. Sometimes they may cause loss of data, and we don't like it with the secondary storage. So what is the solution? The solution is this. With the journaling file systems, most of the file systems nowadays that we are using are journaling file systems, by the way. Okay, so journaling file system says that on a special place on your desk, it says that I am going to do this and this and this. So you put your plan for the disk modification, disk access, on a special place on your desk. First, you write it. And then every time when you do something, I did this, check. Okay, I did this, you check it. And I did this, I check it. I did this, and I check it. When you are done with all of them, then you say that I am done with this operation. So I remove my plan of doing those stuff. If a crash happens before I did this, when I reboot my computer, when I look at that plan file, I see that I did this one, but I didn't do these. Okay, so what would you do? Either you continue doing these or you undo these two. So you always that way you always keep your file system in a consistent state all the time. So you are keeping like a journal. Okay, you are keeping like a journal. What's a journal? In Turkish, maybe you could say seyir defteri. Seyir defteri, like those ships on sea. Okay, whenever they do something, they keep a journal of it. Okay, if a crash happens, if they find the seyir defteri or the journal of the ship, they know what they were doing the last time, or they keep these journals for the airplanes too. Sometimes automatically, sometimes written by the operators. Okay, and we are doing the same thing with the file system. And NTFS, I think I'm using NTFS on this computer, or the Linux ext3, the newer ones. Resilient file system, they are all using the ideas from this journaling. Okay, good. Any questions?
Yes, I have a question, sir.
Sure.
If we go down to the three steps a little bit below, so we first remove the file from directory, remove the inode from the pool of inodes. Didn't we say that the inodes are like limited in quantity? So not every file gets an inode, only the open file gets inodes?
No. We said that every file should have its own inode. That's it. Okay, but you don't keep your inodes in your memory. Only keep the inodes of the open files in your memory.
Okay, I think I misunderstood that part.
Okay, every file
Okay, so
should have an inode because in Unix we keep our metadata file attributes in inodes.
I see now. That now I understand. Thank you, sir.
Okay, so we will discuss this inodes again when we look at this Unix system 5. And I think it will be clear. Okay, good. Any other questions about journaling file systems or log file systems? There are many file systems. Each one has a different property. Of course, when the file systems gets more enhanced, more complicated, it can do many new stuff, many useful stuff, but the file system gets larger. When the file system gets larger and more complicated, it would be difficult to implement them on small systems and embedded systems. Also, the compatibility of those systems would be difficult. That's why for some systems you need to have very advanced file systems, complicated state-of-the-art file systems. Sometimes you sometimes you prefer the file systems of the 1980s, like the FAT file systems, for simple embedded but not critical devices. Okay, and the to complicate things even further, the computer system or operating system designers, they design their operating systems, and sometimes they design their own file systems because they can take advantage of the file system. So that would introduce many other types of file systems too. Just open the Wikipedia file systems. Open the Wikipedia file system stuff, and you're going to see that uh, tons of different file systems, popular file systems. Okay, for the Unix file systems, the inode idea comes from the Unix file systems, and each Unix file system may have their own file system. For the Windows, we have the FAT, and TFS is the new one. Okay. List of file systems. Do I have the file system fragmentation? Do I have the list of file systems? I No, I don't have it. But you are going to find it.
See, oh, there is list of file systems.
Oh, okay. So see, there is a fault tolerant file systems. Like journal file systems is one of the examples of fault tolerance file systems. Oh, this is a distributed one. What's a distributed file system? You don't keep all of your data in the same hard disk or hard drive. Okay, different kind of stuff. So with fault tolerance, these are the ones. Okay, so this resilient file system, we have seen it already.
I have a question.
where is my NTFS? I didn't see it. Okay, what's your question?
When we delete a file, removing a file, what about subdirectory in this directory? This mean really removing all this directory? I don't understand the recursively or.
Well, in this example, we assume that we are removing a regular file, not a directory. Removing a directory is a special thing, and most of the time, the operating systems do not allow you to remove a directory if it is not empty. They say that I cannot remove this directory because it is not empty. So as a user, as a program, maybe you need to go to that directory and remove all the files one by one. After that, you can remove the directory. So removing a directory is a special thing. It has to be done very carefully. Okay,
Directory is also file. Oh, okay.
a directory is a file, sure. A directory is a file. Okay, since you are asking this related question, let me go to the.
Sir, I
Uh,
didn't get why we cannot delete directories. We've done it many times. I think I am understanding something different when you say directory.
I didn't say you cannot remove directories. I said that it's a special operation. And most of the time when you try to remove a directory, the operating system tells that, okay, this directory is not empty. I am not removing it. Are you sure? Or you need to use, for example, if I try to remove a directory that doesn't that has files in it, it will give you a warning, and I am not going to remove it. And you need to use a special flag saying that, okay, I know what I am doing. Remove this directory anyway. In that case, the system has to repeat all the file removal stuff for the all file removing steps that I showed you. So removing a directory is a more complicated thing. You cannot do it in a single step. So you need so that means that a journaling file system is needed if you like to keep your data in a consistent state in case of crashes while you are removing directories. Okay. So back to the original question again. Yes, this is the root directory. This is the root directory. And in the root directory, all you have is the names of the files and their inodes. Okay. For example, the inode number 6, USR, user directory. All you have is the user, the name user, okay, USR, and the inode number. When you come to inode number 6, okay, you have the file attributes of that file, and when I look at it, I see that this is a directory. Okay, now this one tells me the block number, and the block contains all the directory related stuff. Since this is a directory again, I have the names of the files and the inodes again. Okay, so each file should have an inode, and that inode is listed where that file belongs to as a directory. Okay, inside the inode, I have the block addresses of the file. Okay, and remember what we did. If you don't have enough number of block addresses inside the single inode, then you have a last pointer that points to another block that contains additional block numbers. Can I find it? I think I can. I think I showed you this. Yeah, here it is. Okay, so this is my inode. Inside my inode, I have my file attributes, the long file names, and the owners and the permissions, etc. Then I have my block numbers. And the last one is, if these block numbers are not enough, if 7 blocks are not enough to keep all of my data, then I have additional blocks. Okay, so that's what we said last time. So, and where do I keep all those inodes? Inodes are special. Okay, remember this one, this partition. Okay, file system layout. This particular partition is a Unix partition, and it keeps the inodes. Inodes are kept in a special place in my desk. Okay, so inodes are kept separately from the file blocks and directory blocks. Okay, and so these are the limited number of inodes are limited. And usually, how many inodes do I need for this file system? When you are, if you if you if you install the Unix system, usually it asks you the size of the partitions, and sometimes it will let you choose your number of inodes for that file system. So it's a resource. You don't want to keep a small number of inodes or very large number of inodes. Okay, but the idea is for each file you need an inode, and you keep your inodes in your memory if the file is open. Okay, good. Let's go back to the discussion of the journaling file systems. Where are my, okay, so good. Are there any questions? Okay, I continue then. We keep talking about many types of file systems, and usually with our computers we don't keep a single file system on our computer. There are many file systems, and their file system types are different. Okay, for example, for Unix, Unix says that I am always going to have a I am always going to have um, a root file directory. Okay, underneath there is the user, there is bin, there is source, etc., and there is a mount directory. So you always start with the root directory. That's it. That's the idea for many Unix systems. Windows is a little bit different. Windows says that, okay, you don't have to keep a single root directory. You have the drive letters. You have your C drive, D drive, and E drive. Your C drive, D drive, and E drive might have different file systems. This could be a NTFS file system. This could be a CD-ROM file system. This could be a FAT file system. So as you see, I am keeping different file systems on the same computer. How about the Unix? Unix says that, okay, I'm going to keep them under the same directory, but under the mount directory, you may mount your USB drive or a new HDD1, etc. So you keep your new devices under this mount directory. Okay, so Unix makes an attempt to show all the different file systems as a regular file structure or directory structure. Okay, so the idea is this: you have to live with different types of file systems, even if they are very different. Some of them are inode based, some of them are FAT based, some of them are journaling file systems, some of them are not. So how do I manage all these kind of file systems? The idea is using virtual file systems. As a user for me, all I do is, as a C programmer, I use the POSIX interfaces to open files, to append the files, to close files, delete files, move files around, etc. That's what I think. Okay, but the real opening operation might be very different for different files on my system, because I may have a file system 1, file system 2, and file system 3. Okay, so different file systems has to be opened the files on a different file system has to be opened in a different way, because some of them are inode based, some of them are FAT based, right? So as a user, I shouldn't be dealing with these kind of complications, but I should have some kind of a file system. Those are called virtual file systems. And whenever I issue a command, maybe this picture is a better one. Okay. In my process table, of course, I keep the open files in my process table. Each process has its own open files. Okay. And each open file has a pointer to not inodes but the vnodes in this implementation, virtual nodes. Okay. For each file I have these virtual nodes, and depending on where that file lives on my system, different file system, their open read write operations are going to be different. Okay, are going to be different. Okay, so this is like the virtual functions of object-oriented programming languages. You need to run a different open function, close function, read function, write function for different files. So where do I get those functions? I get these functions from the function pointers of that vnode of that specific file. Okay, using this kind of an idea, as a user, I don't have to know what kind of file system I am working on. Sometimes it doesn't make much sense to change the permissions of a file for some file. For example, there's read, write, execute permissions. In Unix, I have read, write, execute permissions for 3 different types of users: the user itself, the group, and the others. In Windows, we don't have this. Okay, this is not that. It is not that easy to represent these, but sometimes I have to ignore it. I have to. I have to ignore it. Okay, and that would be the task of these virtual file systems. Okay, any questions on the virtual file systems? So the interface between the virtual file system and the real file system has to be implemented. The file system itself doesn't know anything about the virtual file system, but the virtual file system has to translate all these kind of user commands, okay, user functions, to the real file system. Good. Okay, let me move to another topic. We talked about this. How do we make the decision on this block size? How large should our blocks be? How small they should be? Okay, and let's make a discussion about it. Okay, if what happens if the block size is small, and what happens if it is large? Since I am asking this question, there should be a trade-off, right? If the block size are too small, too large. Okay, if the block size is too large, we waste space. Why? If the block sizes are too large,
Because that would be like the least amount of data that can be stored over there.
yeah, even if you have a single byte of data for a file, you need to have its inode, right? And you need to have at least one block allocated for that file. So rest of the block is going to be wasted. So that's what we call internal fragmentation. The same idea as the page size. Remember, with the page sizes, if the page size is too large, many large portion of that last page is going to be wasted. Okay, so internal fragmentation. If it is too small, what is the problem? If it is too small, we are not wasting rest of the block. But if it is too small, then I have to keep indexes to small block sizes, small blocks. That will increase my index address bits. Okay, if I have 2 to the power 10 blocks on all of my system, each block has an address of 10 bits. So if I have 2 to the 20 blocks in my system, and each address has to take 20 bits now, okay, and that's going to be wasteful. Also, since blocks are distributed over the disk, and if I have a mechanical drive, so what am I gonna do? I need to make lots of hard drive head movements around, and that's going to take lots of time, and also it's going to take some space. So it has to be in between. It shouldn't be too large, it shouldn't be too small. But how should I make this decision? How should I make this decision? If we have very large files all the time, okay, if we have very large files all the time, then it should make sense to keep our block sizes large. But who's going to make that guarantee? We don't know. Okay, so let's going to look at this idea. Okay, so um, before discussing these, let's look at this picture. Okay, this picture is very old, but it will give you the idea. Okay, they took the statistics in two different snapshots of the same system. Okay, it's called the VU system in some university. In 1984, they looked at the whole file system. Okay, they said that in 1984, 14% of all the files have a size of 128 bytes or less. Okay, so like 15% of all the files, okay, on the file system, their length is 128 or less. This was in 1984, a very long time ago. But after 20 years, they did the same check again. They did the same check again, and they found that only 8% is 128 bytes or less. If I do the same statistics again, okay, if I do the same statistics again, I don't think that more than 2% will have 128 or less. Okay, so that means what? As the drives get larger, our files are getting larger too. So it doesn't make much sense to use a block size of 128 bytes anymore. Okay, so it depends on the time or the hard disk capacity. But when it comes to web servers, their file systems, on the web, things are different. Even though I am using large disks, okay, on the web, for some reason, files are smaller. As you see, almost 30% of all the files have a length of 128 or less bytes in them. So this gives me an idea. The idea is this: I cannot choose a fixed file block size. Okay, maybe it should depend on the file system, or maybe it should be a parameter from the file system. And that's what we are going to see. We are going to see that if you are setting up a new file system, the system usually will ask you what is your block size, and you make that decision. Okay, whatever your decision is, okay, whatever your block size is, you always try to do this. You try to keep your n consecutive bytes of this space for a single file. Okay, so even if your file block size is small or large, you try to keep them in a consecutive way, in a contiguous way. If it is not possible, you divide your files into two separate consecutive block sequences. Okay, so these two is always going to make it better for you in terms of access speed. Not maybe a waste space, but in terms of access speed. Okay, good. So I didn't give you any numbers. I said that there's a trade-off, and trade-off is usually determined. Trade-off usually determined by looking at the simulation results. The maybe looking at some numbers, this trade-off is going to be more clear, and we are going to repeat this actually. I think I showed you this before. Maybe I should erase what I had. Yeah, what I had drawn here. This is a typical mechanical hard drive. There are three platters, one, two, three platters, and I used to keep a mechanical hard drive somewhere on my desk. Can I find it? Can I find it? Yeah, I think I can. Okay, this is a mechanical hard drive, and this is the read-write head here. Okay, read-write head, and this is the platter. It is spinning very fast usually. Okay, and I have only a single platter on this one, if you can see it. It's an old hard drive. Okay, and usually this one works in a vacuum or in a chamber filled with special gas that doesn't chemically interact with the rest of the system. Okay, so this, if I look at one of the platters, this read write moves in and out like this. It moves in and out. Okay, since this platter is spinning in one direction or other. Okay, I can position, if I like to read this part, if I like to, let's say, read this track here. So what do I need to do? I need to spin this. I need to spin this like that, and I need to move my read write head inside in, and two mechanical movements. One, the rotation of the disk. The other one is the linear movement of this disk head, and I will read my data that way. That's what happens. To make things faster, okay, you put many platters on top of each other, and there is a read write head for each side of the platter. So if I have three platters, there are six read write heads, and they always move in synchronization. They are not allowed to move in. They are connected to the same motor. Okay, linear motor. Okay, so let's get these numbers. Let's say a disk with 1 megabyte data per track. So this is a track, right? Track is this. This is a track. Okay. Each track contains 1 megabyte of data to the power 20. Rotation time of 8.33 milliseconds. 8.33 milliseconds. So every rotation needs this much time. Okay, and the average seek time is 5 milliseconds. Question: why didn't I say average rotation of 833, but now I am saying that average seek time? Seek time is the movement of the head from one position to another position. Why don't we talk about the average rotation time, but we are talking about the average seek times?
Well, the search time for the memory
memory location is not defined by the rotation time. It is defined by the seek time. It can be more than there's a error margin for that 5 milliseconds, but occasionally it's average 5 milliseconds.
Rotation is always fixed. I mean, to rotate a disk for one full rotation, you need 8.33. Okay, that's it. You cannot do anything less and anything more. But seek time, when you move your head in or out, you don't always seek from this position to this position. It changes, right? Sometimes from to here, sometimes here to there, sometimes here to here. Okay, so you take the average of all the seek times. Okay, so we talked about the average seek time of 5 milliseconds. Then let's talk about how much time I need to get some data. Okay, I need to read a block of
Sir,
k
I have a
bytes.
question.
Okay,
What is the equivalent of seek time in solid state drives? We don't have a
no,
rotational.
in solid state drives, we don't have any rotation time or the seek time. Okay, the solid state times are given to you like the memory access times. Okay, so doesn't matter where your data is on your solid state drive, you always have the same amount of time delay. And if you remember, I think I gave you those numbers. When we look at this memory stuff. Let's go back to those nice table of universal latencies for a computer system chart. Where are those? Yeah, here it is. So a main memory reference is 100 nanoseconds. Okay, we are not talking about we are not talking about milliseconds, we are not talking about microseconds, we are talking about nanoseconds. Okay, so a memory reference is 100 nanoseconds. If you like to read from your SSD, okay, 1 gigabytes of SSD reading is going to take 150 microseconds. Okay, that's 1 gigabyte of SSD. So that's 1 gigabyte of random read. Sequential read of SSD 1 megabyte. Oh, sorry, this is I'm reading 1 gigabyte per second SSD. Sorry, let's look at this one. This is better. Read 1 megabyte of sequential SSD 1 millisecond. Okay, so 1 millisecond, 1 megabyte, and this is 100. So it is like 10 times more expensive reading it from the SSD than reading it from the mechanical drive. It is much closer than reading from the mechanical hard disk. Okay, because the disk seek time is 10 milliseconds now. So 1 megabyte of reading from mechanical hard drive is 20 milliseconds. From SSD it is 1 millisecond, so 20 times faster. And this is sequential, by the way. Sequential means that you don't do much read write head movements. Okay, good.
All right, thank you.
Let's go back. So I like to read k bytes. Okay, read a block of k bytes. So what do I do? To read the k bytes, I need to move my head. So every seek time of 5. So this average seek time of 5 is this one. And then I need to wait until my data is under my read write head. So the full rotation is 8.33 milliseconds. So on the average, I have to wait half of this time. So 4.165 milliseconds is the average rotation time. And then since uh, since I am reading the whole track, okay, my whole track is 1 megabyte, right? So to read the k bytes out of 1 megabyte, I need to spend k over 2 to the power 20 times 8.33. If my data k bytes is 1 megabyte, then this is going to be 1. So I need to wait whole 8.33 milliseconds. Okay.
But
So
this is assuming our data is contiguous, right?
yes. The time is millisecond to read a block of k bytes. A block of k bytes. So it is a block. Block is by definition continuous. We are reading a block. Okay. Our block size is k. Understand? To read a block out of your disk, you need to do the seek, you need to do the rotational delay, and you need to read. Okay. So when I change k, this is going to give me the total time to read a block. Okay. So if I change this k, what's going to happen? I will have larger k means that uh, larger k means that efficiency. Why? Because to read k bytes, I don't have to spend that much time because I am going to need larger amount of disk space, and compared to this reading this larger amount, these two numbers will get smaller and smaller. But if k is small, then just to read the small amount of data, I need to do the seek, I need to do the rotational delay, and etc. So let's try to draw a graph. That tries to show you how fast it will be to read these k bytes, your data transfer rate. Also, how efficient you would be using this case. Okay, so let's look at this graph. Okay, this is directly from the book, but it looks like I'm out of time for there's a way out of time for the first part of the lecture. Let me keep this graph on my screen. Let's take 10 minutes of break. After the break, we will talk about this graph. So let's be here around 11:42. 10 minutes of break. Efendim? Tamam. Ne oldu, verdin mi? Camını birazcık açık bırak. Şey yapsın. Kaç lira verdin? Toplam. O arkadaki şey çıkmış mı? Orada bir yer var diye bir kişi kendine dökülmüştü. Hangi kartın? O eşekler. Nereye düşmüş? Ona dikkat edin, yapışacağız bunu tekrar. İyi oldu. Hadi görüşürüz. So this is the this is the graph that we draw using this formula. Okay, the formula is this. Let me try to write the formula here. 5 plus, let me use very approximate values of these 4 plus, so why don't I say this, 9 plus k over 1 mega times 8. Okay, so that's the formula. So to read k bytes of blocks, okay, you need this amount of time. I have to get this 9 all the time because that's average seek and average rotational delay, and k over 1 megabyte times 8 the rotational read speed. So this graph shows that the red part, the red one, shows my data rate. Okay, if k is small, this number will dominate. Okay, if k is small, just to even read 1 kilobyte of data, you need to spend 9 milliseconds for seek and rotation, and you read your data. So when k is small, the block size k, 1 kilobyte, your data rate is very close to 0 megabytes per second. So it's going to be close to 0 megabytes, between 0 and 1 megabytes per second. Okay, when you make your k larger, for example 4 kilobytes, 16 kilobytes, 64 kilobytes, then your data rate is going to be increasing. When your k is very large, for example 1 kilobyte, okay, so you are spending most of your time in reading your useful data. So 1 megabyte over 1 megabyte is 1, and 8 milliseconds is all the time you need to read the whole track, plus this one. Okay, so you are always spending the seek time and the one full rotation to read the 1 megabyte of data. So you will be very efficient. So why don't we use k of 1 megabyte all the time, because that will make our data rate maximum 60 megabytes per second. But if you make your block size 1 megabyte, what is the problem with that one? The problem is this. Problem is, even the smallest file will occupy 1 megabyte of this space. Let's say your file is 1 kilobyte and you are occupying 1 megabyte of this space, then your this space utilization will drop. Okay, and this one, let me use it with this green line. Okay, if you have 1 megabyte blocks, then in that case you are going to waste most of your disk space for internal fragmentation. At the other end, if you have 1 kilobyte block size, okay, and by the way, this one assumes that all the files are 4 kilobytes each. Okay, there is no wasted disk space due to internal fragmentation, because all the files are 1 kilobyte each, 4 kilobytes each, so you need 4 blocks. So it looks like 100% disk utilization for 1 kilobyte, 2 kilobyte, and 4 kilobyte block sizes, because all the files are 4 kilobytes each. Then when you make your block size 8, then half of your see this one, this is 8, and 50% of your disk space will be wasted for internal fragmentation. Okay, so it's a nice graph. This will tell you there is a trade-off, speed versus the disk space utilization. You cannot achieve both of them. You need to make sacrifices. Okay, any questions on this graph? Question for you. Is this point critical? The point that I marked with red, now with blue. Is this point critical, the intersection of these two curves? What is the meaning of that point?
So, I think it is important for the memory allocation strategy for new data.
Shouldn't that be the block size?
I think it is where they intersect the writing of data and reading it, maybe.
No, that point has nothing, no critical importance. It's just a, I mean, this part is this space utilization, right? On the right. On the left is the data rate values, okay? And one is a percent, the other one is a megabit per second. Since they are not using the same scale, this point doesn't have any meaning, okay? Just two different curves shown on the same graph, and that's it. So that will not give you the what should be my k is, okay? Just a point, just random point, doesn't matter. Okay, so I mean, look at this one. 60 is the maximum right here, 60 megabits per second. If I choose my maximum as 120, the position of that point is going to change. Okay. Another issue that we need to be careful about, or maybe we should spend some CPU time, or maybe brain time of ours, keeping track of the free blocks. How do I keep track of free blocks? Where are the free blocks? Okay. Remember again, let me try to go to that picture again, our sample Unix file system. Where is that file system? Master boot record. Free space management. Okay. inodes. Okay. So in the free space management, I am keeping the track of free blocks and free inodes. So how should I keep this free list? Okay. Again, I think we did this with the memory. We did this with the memory. Okay. We could use a bitmap. Each block has a 1 or 0. Okay. Each block has a 1 or 0. If it is 1, it is occupied. If it is 0, it is not occupied. I could use a bitmap approach or a linked list approach. This linked list approach lists all the free blocks. These are all free. Okay. I have a block. Inside this block, I have a list of all the free blocks, and then I have a link to the next block of free blocks, and it goes that way. Okay. And the negatives and the positives are negatives, and the advantages and disadvantages for both is already we know, because we did already we did almost the same thing for the keeping track of the memory pages, which ones are free, which ones are not free. We did the same thing there. Okay. Different file systems use different ideas. Fat-based systems usually use these kind of systems, this kind of stuff. Of course, keeping this in memory is going to take lots of space if your disk is large, and depending on your block size, this table will get large or small. Okay, good. We will come back to this picture again when we try to do the disk consistency checks. Quotas are always a problem if you have a multi-user system. If you are sharing your system with other people, and you are not, of course, you are not allowed to use all the disk space. You have to be respectful for the others, but sometimes the system has to stop you from using too much disk space because that space is needed by many other people. So those are called quotas, and the quota has to be, of course, what is the responsibility of the operating system? Abstraction of the underlying hardware and management of the resources. While doing this management, you have to be fair between the users and the processes. So the management of this space between the users is done by the operating system. Operating system keeps quotas, okay, for each user. And I am not going to talk much about the details of this quota stuff. Okay. Backups are important. Remember, the main idea of using the secondary storage is a permanent storage. Okay. The data that you are keeping on your file system is permanent. That's what you assume, and you should not lose your data. But computer crashes, hard disk crashes, and computer crashes, hard disk crashes, and similar problems always exist in computer world. So we have to be cautious about keeping our data safe. So taking system backups is important, and taking the system backup, the mechanism of at least, has to be done by the operating system. So how do I take the backup of the whole system? One idea is this: make copy of all the files, or better yet, copy all the bits that you store on a mechanical hard drive, bit by bit, one by one. Okay, so this would be the simplest. Okay, I have a hard drive here, a hard drive like that. Okay, a second hard drive like that. So keep transfer all the bits one by one, transfer all the bits one by one from one drive to the next drive. Okay, and that would take the backup. That's it. But the problem with this one is I don't have to take the backup of all the files. For example, there are many temporary files on my system. There are some device drivers, okay, and they don't have to be backed up. They are all constant, okay. And if I am taking the backups every night, I already took the backup of the system last night. Why do I keep taking the backups of already unmodified stuff? Okay, maybe I should take the backup of modified stuff all the time. Okay, so incremental backup, that's called. Okay, only take a backup of changed files. Okay, so that's another one. Also, when I'm taking the backup, maybe I should compress my stuff. And when the system is running, usually you don't stop your system from working. System runs, and while the system is running, while people are modifying your disk, you are taking a backup. That's going to be a problem. And the security problem, okay? You should not lose track of your backup data, because that's your data. If somebody with a bad intention, accidentally or on purpose, gets a hold of it, then you are in trouble. So backups are important, but you should be careful about the backups. So let's see one example of backup, for example, for the Unix system. Okay, but before that, do I have any points that I missed for the physical dump? Physical dump is this: physically you copy everything from this hard drive to this hard drive. That's the backup. Okay, physical dump. You start at block number 0 of the disk and write all the disk blocks onto the output in the other one. Okay, so this one is backing up all the unused disk blocks too, because it doesn't know what is written in there. Okay, it doesn't know anything about the file system actually. It is doing the bits one by one. And the bad blocks, mechanical hard drives from time to time, okay, they go bad. When they go bad, the whole hard disk doesn't go bad. It says that, okay, for some part of the disk, for example, this part, it is bad, and this one is bad, and this one is bad. Okay, those are the bad blocks. And the computer system, the file system, understands that these blocks are bad because whatever I write to them, I cannot read the same thing. These are bad stuff. So I keep them marked as don't use these places. Okay. So these physical dumps, they try to take the backups of all those places, and that's not a good thing. That's not a good thing. Okay. Backing up, okay, unused places, or backing up bad files and etc. They are fast, but I mean, they don't have to make any decisions. They are physical dumps. They are stupid dumps, but we need to be more smarter to make it more efficient. Okay, so we are going to do the logical dump, not physical but logical dump. Okay, a simple algorithm for this one is this one is given here. Okay, so starts at one or more specified directories. You say that take the backup of this directory, not the whole hard disk or whole file system. So if I like to take the backup of a single simple user, then I can say that, okay, take the backup of this directory, okay, and recursively dumps all the files and directories found there, okay, that have changed since some time given base date. After this date, whatever is modified, then take the backups. Okay, directories are special though. Okay, directories are special. All the directories that lie on the path to a modified file or directory, you need to take the backup of it. Okay, you need to take the backup of it. For some reasons that will be clear later. Let's look at this example. Let's say this is our file system. There is a root directory. This file is modified. These two files are modified. This file is modified. Okay. These two files are modified. This directory is modified. This directory is modified. So what is the difference between, let me, okay. What is the difference between this one and this one? inode 20 and inode 2. This one says that this directory is not modified. This one says that this directory is modified. Can you tell me the difference? Why didn't they mark 2 as modified and 20 as modified?
I didn't understand the question. What do you mean? Why didn't they mark 2 as modified?
Maybe I should ask it this way. What is the meaning of a modified directory?
Something about its attributes has changed?
Explain that a little bit.
Like, we changed its name, we maybe copied a file into it, we changed the like who can modify the
exactly.
it.
Yeah. So if you modify the directory, change the name of it, change the access permissions to it, you modified the directory. Or if you added a new file to it, you modify the directory. But if you modify a file inside that directory, you are not modifying the directory, right? So you change this file 3, you renamed it. That doesn't mean that you modified the directory itself. This one, it looks like somebody has added this file 21 to this directory. Since you added a new file to that directory, you have changed it. So those are different. So this algorithm says that when I am doing the logical dump, logical backup, of course I need to write this one, all the modified files and directories to the disk, but also you need to write this one, this one, this one, this one, this one, here, here, here. All the ones that I marked with red, they also has to be written to the desk, even though they are not modified. Why? Because if I am going to write this to the desk, take the backup of it, okay, I need to store its path, okay. How am I going to store its path? I need to put this in the desk, and this one, and this one, and that one, okay. So that will make my job a lot easier. So that's what we were saying, that, okay. Dump all the directories that lie on the path to a modified file or directory, because, okay, they transport the entire file system between the computers, and to make it possible to incrementally restore the single file. If somebody says that, okay, get me 8, I take a backup of it last night, so when you get 8, you need to know that 8 is under 7, 7 is under 6, and this one, etc. Okay, so let's keep this in mind, and our algorithm is going to do that. So this is the algorithm in 4 phases. Phase number 1, for each modified file, its inode is marked in the bitmap. What does it mean? It means that, remember, there is a bitmap representation of all the nodes. I say that, okay, for each modified file, I mark their inodes in the bitmap. There is a bitmap for the inodes. Maybe use a different color. Okay, these are inode bitmaps, and there is block bitmaps. Those are 2 different things, right? So first you go to the inode bitmap, and for each modified file, I mark them. So you say that, okay, I mark this one, this one, this one, this one, this one. I mark them. Also, each directory is also marked whether it is being modified or not. So this one marks all the modified files, all the modified directories, also every directory in this inode bitmap. Okay, so the reason why we are doing this will be clearer, although there are many other ways that you can do it differently, but this is the algorithm that I had chosen. Okay, so phase 2, walk the tree again, unmark any directories that have no modified files or directories in them. So you go back and you say that, okay, this directory doesn't have any files in them. This directory doesn't have any modified files in them, okay? Or this directory is not on the path to a modified file. So you are undoing some stuff with the inode, and then I do the inode scanning of the inodes in numerical order and dump all the inodes to the disk, and I do the same thing with the files that are marked, also dumped, again prefixed by their attributes. Okay, so the inode dumps and the block dumps, first I do the directories, then I do with the files the same thing. Okay, this is the file system backup. Let me show you an example. Let's say these are I am not going to look at the blocks for now, and I am going to look at the inodes only, but dumping of the blocks are exactly the same thing. Okay, so the phase number 1, this is the same picture. Okay, the phase number 1, it marks all the inodes of all the files, also inodes of all the modified files, also inodes of all the directories. So as you see, the 3 is marked, 8 and 9 is marked, 17, 21, they are all marked. Also 1, 2, 5, 16, 18, they are all marked. All the directories and all the modified files are marked. That's the phase 1. In phase 2, you go back and you unmark all the directories that don't have any modified directory in it or any modified file in it. So I go back. Let's look at number 10. Number 10 doesn't have any modified files under it or all the way to the bottom. So number 10, number 11, number 14. So 10, 11, and 14 are gone because they don't include any modified files and they are not modified. This is the second phase, and then I scan this table, and I dump all the directories to the disk. So I dumped this one, number 3, and then 8 and 9, and then 17. So I dump all the directories, and I come back and I dump all the files, the inodes of the files. Of course, I have to do the same thing for the blocks. Dumping the inodes only doesn't make any sense because inodes don't carry any file data. Okay, inodes carry metadata and the block information. Good. Okay, so this is how you do the file system backup. File system backup. Logical backup, of course. Logical backup. Any questions? Okay, if there are no questions, let me continue. As I said before, we should be very careful about the consistency of our file system. Okay, with the help of the journaling file system, we try to keep everything consistent, but from time to time, due to mechanical failures, due to software bugs, due to many reasons, our file system could get inconsistent. What do we mean by inconsistent? For example, could this happen? Yeah, this could happen maybe. Let's go back to this picture, the picture of how we keep the, okay. These are the block numbers of the free blocks, right? Block numbers of the free blocks. Block number 262 is free, is listed as free. But if I look at the inode of some file, it lists the block number of the first block as 262. So one of my files says that the block number 262 is occupied by this file, but in my free disk blocks it is listed as free. So this is an inconsistency, right? So what are we gonna do? I cannot ignore this fact. I said. So what would be your solution in this case? A file says that this block is mine, but on my free disk blocks, I list it as free. So what should I do? Any ideas? I'm seeing the same block number in two places. It is one part of the system says that it is free, the other part of the system says that it is occupied. Okay.
Say it's occupied. Better safe than sorry.
Say it again, Usama.
Is it?
I said I would consider it occupied because better safe than sorry, because maybe like one bit got corrupted.
Okay. So you are saying that just take this number out from this free list? since somebody is listing it as a occupied, then I will take it because a file is owning it. So maybe that's a good idea. Maybe I should also report this to user. Okay, report this to user saying that I recovered this file this way. Probably this file is corrupted, but I saved it, and I am warning you that there might be a problem with this file. You could say that too.
Sir, can the exact opposite of this happen? It is actually free, but it looks as if it was full.
Yeah, well, I mean, whatever happened. We don't know. I mean, there is no way, if the file system is not a journaling file system that can keep track of everything that you did for the last 2 days. Okay, there is no way to recover that information. Maybe it is really free. Maybe the corrupted file is that file, but I think the better idea is I recover such a file. The blocks of that file is listed as both free and both occupied. So I am saving this information somewhere. As a user, you just check this file. If it is meaningful, you keep it. Otherwise, you delete it. Then it becomes a real free block. Okay? And if you run file system check, on Windows or on Unix, it produces lots of files, right? Do you know that, right? It produces lots of files. The recovered files, you say that I recovered these files. I don't know what they are, but I recovered them. So you check them, and if they are meaningful, you keep them. Otherwise, you delete them. File system checks are doing that. Okay, let's try to see. There are many combinations of these kind of inconsistencies. Let's try to see some of them. Okay, this is what we do for all the blocks in our system. Okay, for all the blocks in our system, we check them. Okay, if that block is listed as free block, then I mark them in the free block table. This is a special data structure that I am using now for file system consistency. Okay, and I scan all the files and I mark if that block is used by any of these files. So what I'm expecting is that a block is either free, okay, like this one, or occupied. So it is not possible to have two things happening at the same time. A block cannot be both free and in use. Or you cannot say that the block is not free and block is not used by anybody. So 0, 0 is not possible. 1, 1 is not possible. It has to be either 1, 0 or 0, 1. So this is a nice picture. This is a picture that we like. It always has to be like that. This is a picture. What is the problem with this picture? This one says that block number 2 is not free, but I couldn't find a file that uses this block. Okay, inconsistency. This shouldn't happen. So what would be your solution? What is your solution for this one? Remember, I am not asking the question of what happened. I mean, how could this happen? I don't know. It's just an inconsistency. This cannot happen.
Consider it free.
Consider it as free because no file claimed it. So what am I gonna do? I mean, I cannot append this block to some random file. I am going to consider it as free. So what I am going to do, I am going to move it to free. Okay, this is what I do. How about this case? What is the problem with this case? 101001. Oh, okay,
It's free twice.
yeah, it is free twice. How could this happen? Well, this cannot happen with the bitmap free list, right? This cannot happen with the bitmap free list, but it would happen with the free linked list. Remember the free linked list? You will say, okay, number 2 is free, number 4 is free, number 4 is free again. So, I mean, what's going on here, right? So you cannot list the same block free 2 times. That's going to give me trouble, because when I need this space, new block, I will take this out. Okay, I take this one. Next time the 4 is there again, I will take this 2. Okay, so that will give me the same block for 2 different files, and that will be a problem. So what is your solution here? So my solution would be just take this one out in my free list. Okay, and another one is here. What is the problem? Oh, okay. So how could this happen? It says that a block happens in 2 different files. It's like, let me try to draw the picture. The inode for file A lists block number 5, and inode for file B lists block number 5 as its block. Both of them. Maybe they are sharing the same block, but in that case the system would know that there is a link, hard link or a symbolic link between them, but in this case it doesn't know that, so there is no link. So for some reason, maybe because of this problem, remember this problem? The same block is in the free list 2 times. So one file took that one, the other one took this one. Maybe it happened that way, but I don't know. So what would be your solution? What would you do?
Report to the user.
Well, I would report it to the user, but before that, maybe I should do something. Okay, I'm reporting this to you. I did such and then I see this. So what should you do?
Put 1 to the free box. Declare it as occupied.
Put 1 to the free list. That would be even more dangerous. Two files are sharing the same block. If they are really,
replace it with a link.
This is what I would do. I would make a copy of block number 5. Okay, I would make a copy of number 5 to 14. Okay, I would make 14 now used, and I would replace this 5 with 14, and now this one is going to be 1, right? So block number 5 is not shared anymore, but I copied it to a new block 14, and this file B is using 14 instead of 5. It contains exactly the same information. Its block number has changed. So probably there is a corruption. Probably those both file A and file B are now corrupted. But this is the best thing that I can do. I am trying to save whatever I can save, and I will let the user know that I did such a thing. Okay, at least now my picture of blocks in use and free blocks are now in consistent shape. So this is file system consistency checks, and these could happen. When these happens, these are some of the solutions that we can come up with. I mean, we are not sure why any of these problems happened, but given the circumstances, this is the best I can do. Okay, This is the best I can do. Okay, it looks like I'm out of time. If you have any questions, I can take the questions. Otherwise, I will stop at this point. Any questions? It gets very detailed. It gets very detailed. I mean, once you talk about the persistence, once you talk about the data being kept forever, okay, we need to be careful about the system crashes and etc. There are many things that can happen, and obviously it is very difficult to take care of all the things. So it gets more complicated than managing your memory or managing your CPU. And usually the amount of code of the operating system to manage your secondary storage or to manage your I/O devices, in fact, in general, is much more complicated. You spend many more lines of code to take care of your secondary storage and I/O devices than the memory system or the CPU system. Okay, the part of the operating system that deals with the memory and the CPU is much smaller in terms of lines of code. Okay, because there are many exceptions, there are many problems that can happen, and we need to be careful. Previously, we ignored all these problems for the memory. I don't care if there is a I don't care if there is an inconsistency in my page table. I can't do I can't do much. Okay, if there is an inconsistency in my page table, then I am done. I need to restart my system. It's a bug. But with the file system, no, that's not that's a luxury to reinstall the whole system again because I need to save as much as I can. Okay, no questions. You guys are so quiet. I have only 3 people talking, 4 people talking. So that's like 3%, 5% of the whole class. Okay, so read the whole chapter tomorrow. We are going to finish up this chapter and we will start the IO chapter. Okay, I'll see you tomorrow.
Have a nice day, sir.
See you, sir.
Bye. Thank you. Bye.